Hey everyone again. Let's continue our discussions of introduction to MIR. Okay, I actually wanted to stay outside to see more posters and demos, but yeah, the organizers asked me to come back. Okay, let's continue. So first, let's continue our discussion on the auditory perception, and then we'll talk about the psychoacoustic experiments. We talk about loudness, right? And one interesting phenomenon regarding the loudness is masking effect. Masking effect happens when two sounds have very close frequency, and then the louder sound tends to mask the perception of the weaker sound. Okay, so let me play several examples. Sound tones. This is a 1000 Hertz tone. And if I play two sine waves together, one is 1000, another one is 975 Hertz, and with a signal ratio of 20 dB, let's listen to it. Okay, the 975 Hertz tone is quite hard to hear, right? If I increase the energy of the 975 Hertz tone to make the ratio only 6 dB apart, you can hear it more clearly. Now, if I change the 975 Hertz to 475 Hertz, so the frequency difference from the 1000 Hertz is larger, and the signal ratio, I still use 20 dB. Right, it's very clear, this 475 Hertz tone. So this masking phenomenon can be described using this masking threshold. So this curve is an absolute threshold of hearing. You know, it depends on what frequency the sound is. For certain frequencies, the threshold is lower. For other frequencies, the threshold is higher. You need the signal to be stronger to hear it. Then this is the masking threshold for this masking tone. So this tone has this amplitude up here, and then any tones nearby this masking tone that has an amplitude smaller than this threshold will not be perceived by the listener. Okay, although the signal is still there in the mixture, but as perception, we cannot hear it clearly. Okay, another important property of hearing is this loudness difference limits. So how small the difference of loudness can we perceive, right? So people did a lot of experiments, and they found that this difference limits is quite constant for the white noise at different sound pressure levels. Okay, you can see that this vertical scale is the intensity plus delta I. Delta I would be the increment of the intensity to create a new sound, a louder sound, and divided by the original intensity I. So this is a decibel scale of how much decibel you increase the sound to hear it, to hear the difference. And you can see that from 20 dB for the intensity up to 90 dB is almost always like 0.8 dB increase, okay, which is about 15% of the original intensity. So the increment should be about 15% of the original intensity for us to hear the difference. If it's smaller than this increment, then we tend not to hear the difference. Okay. Now for those tones, the sinusoidal sounds, the threshold or difference limits are different depending on the sound pressure level we have. So this is the equal loudness curve. Basically, it tries to unify the hearing loudness for different frequencies. Okay. So first, the dashed line is a hearing threshold. For certain frequencies, like frequencies between 3000 Hertz and 5000 Hertz, the threshold is quite low. We don't need the audio to be very strong to hear it. But for low frequencies, like lower than 100 Hertz, we need the audio to be quite loud, quite intense to hear it. And for high frequencies as well. Now, for a certain loudness, for example, 40 dB SPL, okay, you know, the intensity along this curve will give us the same level of loudness perception. Yes.
Sorry, this is a little deviation question, but thought I will just shoot out. Here, energy, we all have, we have, like most of us know this for a long time, very fundamental. But if we define energy in a different way, such as the Tiger energy operator, TEO, does it become more flat? Have you seen it? Have you thought about it?
Yeah, I haven't thought about that.
Okay. No. Because it's a F squared multiplied by E squared, amplitude squared. The Tiger energy operator is proportional to the frequency also. So we can see that lower the frequency, it needs a higher energy for us to perceive.
Yes, yes.
So is this a direct evidence for saying that the perceptual loudness is closer to Tiger energy operator rather than the simple B squared?
Yeah, that's a good question. I don't know. Yeah.
He has also worked in Tiger energy operator quite a bit.
There is actually a paper, citing in the neuroscience, the mathematical modeling of cochlea. In that paper, actually, they have shown that basilar membrane is actually represented as segmental regions where mass spring damper system, each of the basilar, so, with respect to place theory of hearing, that one particular tone will make one particular region in the basilar membrane vibrate. The other region in the basilar membrane will not vibrate. That's the place of theory of hearing. With respect to this theory, we take the basilar membrane as a segment, small segment, and because it is vibrating locally, we model it in the mass spring damper system, which is the second order differential equation. And this differential equation, if we solve, we get a system function in Laplace domain over the frequency response, whose impulse response is the damped sinusoid. And that damped sinusoid has an energy which is function of the damping factor, that is amplitude, and the frequency of the sinusoid. So indicating that even with respect to tone that is given for the excitation for the perception, it also represents in a way the Tiger energy operator in the subbands.
Okay, interesting. Thank you for the remarks. Yeah, this is very basic. So if we measure the sound intensity using the power, and we can equalize the loudness across different frequencies. Yeah. So here we see the loudness unit called the phones, and it relates to this dB SPL unit, which is a physical quantity attribute of the signal. But this phone scale does not tell us how to increase the loudness of a sound by n times. Okay, it only tells us, okay, this frequency, at this frequency and this frequency, you need to have different intensity levels to achieve the same loudness, but it doesn't tell us how to increase a loudness by n times. And to do that, we have to introduce this so-called phone scale. So again, the phone is a unit of perceived loudness to compensate for the effect of frequency on the perceived loudness of tones. And its definition is 1 phone equals to 1 dB SPL at 1000 Hertz. The song unit is a perceived loudness scale, and its definition is at 1000 Hertz, 1 song is 40 phones, which is 40 dB SPL. And a stimulus that is n songs loud is just as to be n times as loud as 1 song. So if we have n song of sound, then it's n times as loud as 1 song sound. So song scale tells us how to scale the loudness. And the relation between phone and song can be described by this curve. It's this relation. So on the left side is the phone difference between two stimuli, and on the right side is a song unit, and this is the relation. Okay. So basically, if we increase by 10 phones or 10 dB SPL, we generally achieve twice as loud as before. So with this relation, then we can draw a relation between intensity and song directly, right? We first have the intensity dB with dB SPL, and dB SPL has a relation with phones, and phone has a relation with songs. So now we can draw a relation between intensity and the song directly. And this applies to tones at 1000 Hertz with an intensity greater than 40 dB SPL. And yeah, I think I need to skip the derivation, but basically the intensity, so if we want to make the tone n times as loud, right, we need to make the intensity n to the 3.32 power as much as before, roughly 8 times intensity as before. So roughly speaking, 8 people talking exactly the same content in phase is twice as loud as 1 person talking. Okay. And that's why in traditional papers, people use cubic root of I, the intensity, as a measure or a description of loudness, of perceived loudness. Yes, pretty.
The subjective loudness, how reliable is the measurement? It's quite hard to ask someone what is twice as loud.
Yes, I found it a very tricky question too. I don't know how reliable it is. So yeah, this is just a result I found from literature.
I could not understand this. You can explain this after.
It's done by relative scaling, like the perceptual loudness. All perceptual measures have the same problem. Well, not only loudness but pitch also. So you give a value and then ask the listener to make it half, make it double, and then make it double and ask him to do half. So it will come back to the original order.
I see.
So you can do this kind of to any number of repetitions you can do.
I see.
You can make it, let's say 100, 105, and then ask him to make it half. Usually our judgment of half and double in perception is considered more reliable than 1/3 and 3 times like that. So half and double are okay. So we move the whole scale, and loudness is fairly easy, which also is fairly straightforward. But timbre, when it comes to timbre, will interfere a lot in these measurements. But we should keep the same timbre. It's like or something, and then take care of it. So audiology people do that quite often, and it's well-established case. We can trust it, but I still can't answer her in a quantifying manner. Is it 5% error, 3% error? What is the error among the population? It's believed that serious listeners in any perception experiment, it has to be a serious listener. So trained listeners, and we cross-check it. I mean, even in our recent thesis work, only 80%, 70% of the serious listeners pass the test. How reliable you are in your judgment, we check it out actually. If they are not reliable, we say thank you. So we go to the other way.
Okay, yeah, thank you for the remark. Very insightful. Yeah, I learned much. So yeah, then we talk about frequency and pitch perception, and there's also frequency difference limit. This is about how much frequency do we need to change so that we can hear the difference, right? Let's take an experiment. So they do this kind of experiment a lot to find out these results. So I'm going to play the 1000 Hertz sound wave and then play 1001, and you can tell me whether you can hear the difference. No difference. Okay, let's try 1000 and 1002. Yeah, yes. No, loudness is the same. No, loudness is the same. Their power is in pitch. I'm changing the hertz. Huh? You hear difference. Yeah, some people hear difference and some people still feel it's difficult, right? Yeah. Now let's listen to 1000 and 1005. This was 1000. Sorry, this is 1005. I'm sorry? This one? No, this is 1000 Hertz. And the last one is 1005 Hertz. Yeah. Oh. I see. Yeah. Okay. So in the research, people found that the difference limit is about 0.2% of the frequency we hear. So 0.2% of 1000 Hertz is about 2 Hertz. So many people can hear the difference between 1000 Hertz and 1002 Hertz. But The difference smaller than that is very difficult to hear. Yeah. So and they do the experiment at different sound pressure levels, and they find a pretty consistent result when the sound pressure level is not too soft. If it's too soft, then we have to make the frequency difference larger to hear the difference. Okay, so then pitch perception. What is pitch? Vipu already gave a introduction on pitch perception. It's according to ANSI, it's the attribute of auditory sensation in terms of which sounds can be ordered on a scale extending from low to high. So it's a one-dimensional percept, pretty much. And it depends mainly on the frequency content of the sound stimulus, but also depends on the sound pressure and the waveform of the stimulus. So this is very abstract. A more operational definition is to compare the pitch perception of the sound with a reference. The reference people take is a sine tone of a given frequency at 40 dB SPL. So you control the loudness and you take the sine wave, and then you find which frequency can match the sound you hear. That's how you determine the pitch of the sound. Okay. And above 500 Hertz, the pitch perception follows this MEL scale. MEL comes from the word melody. So it's basically a logarithmic scale. That means if we want to double the pitch percept, we at a lower frequency, we only need to increase the hertz this amount, but at a higher frequency, we have to increase the hertz more. Right? So it's a logarithmic scale. So yeah, this is a very brief introduction of the loudness and the pitch perception. But we can see we're trying to draw relations between physical attributes of the signal and the psychological perception. Now we know that for a sound, the pitch perception is basically very highly correlated with the frequency, the fundamental frequency of the sound. And it's pretty much a one-dimensional percept. You can order from low to high. For loudness, it's highly related to the intensity of the sound. And it's also kind of one-dimensional from soft to loud. But pitch and loudness are just two attributes, perceived attributes. There are so many more, right? For example, we tend to describe the sound using some subjective adjective words like warm. Say this instrument sound is so warm, bright, or rough, or say this sound is like a violin, something like that. So we know that these terms are describing the timbre or sound quality of the sound, right? But the question is, what are the corresponding physical attributes that we can compute from the signal to characterize timbre? Right? This is the question. And it turns out that this is a very complicated question. If we look at the definition of timbre or tone quality, sound quality, or tone color, it's defined as the attribute of auditory sensation in terms of which a subject can judge that two sounds similarly presented and having the same loudness and pitch are dissimilar. So it only tells us timbre is not pitch, it's not loudness, it's not duration, right? It's something else that we can use to discriminate sounds. Yes.
So the timbre is used for the distinguishing the musical instruments.
Yes.
For the same tone.
Yes.
In a similar way, can we relate the timbre phenomena? Because MFCC are traditionally used for getting the timbre information from musical instrument. Mm-hmm. So then MFCC are also used for getting the speaker specific information.
Yes.
So from the auditory perception perspective, how do we relate the timbre, if at all possible, from the musical instrument versus the timbre-like features can be extracted from the speech or singing or, the audio.
You mean like a signal specific timbre feature?
Speech. Can we associate the timbre feature as it is distinguishing the two musical instruments?
Yes.
So can we use it similar kind of features from the two speakers' voices to distinguish?
Yeah, we can. So
what is that feature called?
MFCC is one typical feature, right? For speaker recognition.
The question was, how do we define timbre-like phenomena to the speaker distinguishing factor? Is my question.
Okay. So then we have to control other factors. which is difficult for.
In short, my question was like, what is the meaning of, like, can we say timbre of speech? Is my question.
Yeah, timbre of speech. Well, in nowadays, voice conversion can kind of achieve that in a synthetic way. So you can control the pitch and the content and the duration of the utterance, but just change the, say, the speaker identity to a different people. It's kind of like a timbre.
So which means that, just as harmonics is derived from music literature, we are also deriving the timbre from the music literature to speech,
Maybe Professor has some remarks.
Yes, it's not used often, but it's the same thing. Like you represented in your earlier talk, the capstone, the notion of a capstone, capstone envelope.
Yeah.
He also know, I'm sure he uses quite a lot. The capstone envelope represents both the vowels and zeros. We know that from second theory. That's a fairly good representation for the timbre of the vowel difference between, let's say, my vowel A and your vowel A. There will be slight differences.
Yeah.
And that is reflected in the capstone envelope.
Yes.
But the music instruments, actually, it's much more complicated. Maybe he didn't refer to it. For music instruments, the timbre itself, it is a short-term phenomenon that we know for R or E, it's a stationary sound. But in the music instruments, when I pluck a guitar or pluck a veena or a sitar, so the timbre changes with time.
Yes.
So it is the evolution of the spectral envelope with time, which is fully, should be called as timbre. Timbre, that's usually, it's the French term. It's a timbre for a music instrument. Yeah. Thank you.
Yeah. 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 So give you examples. Here we have two notes played by different instruments, but with the same pitch. That's and the loudness. Again. Right, same pitch, same loudness, similar duration, but you can tell the difference. And that attribute is timbre. But this definition is not really useful for engineers, right? And actually, I found an interesting PhD thesis in 2000 from MIT. He said that the word of timbre is empty of scientific meaning and should be expanded from the vocabulary of theory and science. And let's look at some other definition of timbre. Helmholtz in 1877 already gave a definition. It says it's the quality of tone or timbre should depend on the manner in which the motion is performed within the period of each single vibration. So he talked about the waveform shape. Okay, you can translate that to spectral shape as well. And ANSI also give a more explanation to their definition. It says the timbre depends primarily upon the spectrum of the stimulus, but it also depends upon the waveform, the sound pressure, the frequency location of the spectrum, and the temporal characteristics of the stimulus. So it's very complicated. Let's look at several examples. So the previous example that we can discriminate clarinet from oboe notes is about the spectral energy distribution, right? Now let's listen to some other examples which relate to the temporal aspect of timbre. So this note, if I cut the attack time of the note out, and it sounds like this. Right? What instrument do you think it is from? Clarinet. Some kind of woodwind instrument? Yeah. Okay. Let's play with attack. Right? Yeah, it's a string instrument. It's a viola. Okay. Let's listen to another example without attack. What kind of instrument? A trumpet? Yeah, some kind of brass instrument. Yeah. Let's listen to it with attack. It's a brass instrument. It's a trombone. Yeah, you're correct. Nice. We can see that attack is actually very important for characterizing the timbre attribute. And also temporal evolution is important. So this is a note played in reverse time. Let's listen to it. What instrument is this? Some string instrument, echo string, yeah, that's played in forward time. Uh-huh.
Sometimes in the mail system, instead of sound, which are attack. Can you also work with ambiguity as a video based system? Or the take this audio, we take this spectrum and corresponding input response. Sometimes the signal that is attack without attack.
In speech, we define something called minimum phase systems.
Yes.
Versus the maximum phase systems, mixed phase systems. So when the system is minimum phase, then the corresponding impulse response will decay quickly. And hence, when we use that to synthesize speech, that corresponds to a kind of a fast attack, where there's a quick onset at the GCI. So like that, if we take this audio, when we are saying the attack, is there any work referring to this kind of whole zero modeling where minimum phase, maximum phase systems are referred in the audio representation?
No, in this example, I just simply try to show that attack is very important for timbre perception. There's no engineering operation under it. So let's listen to the forward time of this note. Right, clearly it's a piano, but when we play it in reverse time, we feel that it's an echo string. So actually, if we revisit the definition provided by ANSI, it says that it's an attribute for us to tell two things are dissimilar, are different, right? But it doesn't mention that we use timbre to draw two sounds together. Actually, we use that a lot. For example, when we listen to music, so we hear two notes, we say that those two notes are played by the same instrument. What attribute do we use to draw them together? It's timbre, right? Mostly timbre. But this ANSI definition doesn't mention that at all. I think that's a deficit of this this definition. For example, I play three notes to you. Which of the two notes are the same instrument? The first two, right? They're of different pitches, but they are played by the same instrument because we feel some attributes is similar. That's timbre attribute. But this definition is not captured by this, right? So what representation we want to get is really first need to be computed from the physical signal, okay? And it need to be able to discriminate different sound sources, say different music instruments, maybe different speakers. And also it need to be approximately invariant to other factors like pitch loudness for the same source, so that we can draw the sound objects generated by the same source together. And there are actually many timbre-related audio features. I would say most audio features are timbre-related, but there's no single feature that characterizes the timbre completely. So that's a complication of timbre modeling. In the last part of the lecture, I will talk about some timbre features and also using machine learning to compute some novel timbre features. Okay, so now let's move on to psychoacoustic inspirations. So there will be some interesting experiments if you are not, if you don't know this yet. If you know, maybe it's a little boring, but it's always interesting to hear some sound examples. So in psychoacoustics, researchers study how humans parse complex audio scenes. Okay, for example, this violin excerpt. Okay, 8 notes, very clear. And when we look at the spectrogram, it's very clear. We see the fundamental frequencies going down and then up, and we also see the harmonics, we see the vibrato, and very clear. But the example I showed you earlier, there are 7 sources mixed together. The spectrogram is really messy, right? But in cocktail party scenarios, we are still able to switch our attention to different sources pretty easily. Right? How do humans achieve this? And this is a study of auditory scene analysis. So auditory scene analysis, the word comes from scene analysis. scene analysis is about visual scene analysis. For example, when we look at this picture, it's a bunch of blocks. And we can tell that this A portion and this B shape actually belong to the same surface of the same object, right? This E and this F and this A, this E and A are very similar in shape, right? But they are of different surfaces of different objects. So this is about scene analysis. We're able to tell the objects from the complex scene and tell the relations between those objects. Now, auditory scene analysis is doing the same thing. So given a complex auditory scene or audio recording, how do humans tell the objects, sound objects, and relations of the objects? This is a very difficult problem. Why? Here's an analogy that Dr. Breckman came up with. So he said that if you go with your friend to a lake, right, and your friend dig two small water channels along the lake so that the water can travel into the channel. Because there's the water waves, right? When the waves arrive, the handkerchief attached to the channels will float, will fluctuate. Okay. So now your friend asks you to only watch these two handkerchiefs, the movement, and tell how many boats are there in the lake. What type of boats are they? Where are the boats traveling to? Is that a windy day? Are there big fish in the lake? Things like that. By only watching the movement of these two pieces of cloth. Okay. This is like impossible almost, right? But it's a strict analogy of how human auditory system analyze sounds. So the lake would be the atmosphere. The boats are the sound sources in different locations and different types. They are moving. They change their timbre. And the waves come into our ear canals, and then the handkerchief will be the eardrum. They vibrate, and then the cochlea will analyze the vibration, and our brain can decode the sound objects. Okay. So auditory scene analysis is to study how human auditory systems solve problems like how many sources are there, what frequency components belong to the same source, how does the source evolve over time, where are the sources, these kind of questions. And through many years of study, researchers summarize the findings into these conclusions. First, they think that we do an analysis synthesis process to analyze the auditory scene. So we first decompose the acoustic scene into small units, time frequency units. And then we have some grouping mechanism to group those units into so-called streams or objects of sound sources. And there are two primary streaming grouping mechanisms. One is called simultaneous grouping, meaning that simultaneous sound objects can be grouped together into a bigger sound object or source. The other one is called sequential grouping, meaning that some objects in a sequence in different times will be grouped together based on other cues into a source. So how to utilize these two grouping mechanisms to analyze a complex scene, pass it into sources or streams is a main concern about auditory scene analysis. And these two types of grouping mechanisms can compete to each other. This example is very interesting to showcase the competition. So first, we're going to hear two tones, BA and then AB. Okay, B is higher than A. Let's hear it. Okay, two tones, very simple. Next, we're going to play these two tones. When AB is played, we're going to play XX as well. X has a much lower tone, 1.4 kilohertz. Okay, but they are about the same time as A and B. Do you hear the AB tones clear still? To me, when BA was played, right, it was BA, that was clear. But then when AB is present, because of the interference of X, they are mixed together. It's very hard to hear the AB. But now let's, in addition to the X tones, we're gonna also play some C tones at the same pitch, same frequency as X, and they're equally spaced in time with X. Let's listen to that. Okay, so now the AB tones are much clearer than before, right? And the reason they explain that is because in the first case, when the C tones are not there, only X tones were there, X tones were grouped together with ABs due to simultaneous grouping. They are grouped into the same object that we cannot tell the AB very clearly. In the second case, when C tones were present, X tones were grouped through sequential grouping into the C tone stream, leaving the AB into a separate stream. So ABs are easier to perceive. So there's a competition between simultaneous grouping and sequential grouping. Yes?
Yeah, so is there a bias towards important like simultaneous grouping, or can we create the reverse examples also when the sequence, is there a bias towards sequencing grouping? Or can we create examples where simultaneous can mask sequential?
Yes, yes, there are many examples. I'll show you. So this is a sequential versus simultaneous, which we should win, right? So it depends on the frequency gap between the simultaneous tones. Also, it depends on the frequency gap between the sequential stream. Okay, let's listen to it. I think we're gonna change some frequency. So we first heard A, B, A, B, A, B. And then we heard A, B, C together. Okay. Which kind of grouping do you feel? Do you feel B and C are grouped together, or B and A grouped together? To me, B and C are grouped together, right? Yes. Now next. B and C grouped together, right? A and B have the same frequency. Okay, in this case, to me, B and A are grouped together, and C is a separate stream. So they can compete. Yeah. Another interesting experiment is stream segregation. So whether we would group these tones into a single stream, or we actually segregate them into separate streams. It depends on how fast we play these tones. Okay, so here we have 6 tones, 3 high tones, high 1, high 2, high 3, and 3 low tones. And the order is always high 1, low 1, high 2, low 2, high 3, low 3. Okay, let's first listen to the slow version. Okay, we can hear the sequence of the 6 tones very clearly, right? Now let's play the 6 tones very quickly. Okay, to me, I hear 2 streams. They're independent. I cannot tell the order of the 6 tones, but I can tell within a stream that the high tones are going down and then cycle. The low tones are going up and then cycle, right? So we achieved stream segregation. And stream segregation was actually utilized by composers, hundreds of years ago. Composers compose music with these fast pitch alternations to achieve 2 streams on the same part music, right? And for example, this piece is a toccata and fugue. It's an organ piece, but this violin player is playing this piece. It's a let's watch it. And I think that's sufficient. So in the beginning, it's always monophonic. At any time, there's only one note, right? But the notes alternate so quickly. And when we hear it, we hear like there are two streams. One is a constant pitch stream. Yeah, this D note, right? The other is the alternating changing pitch stream. Okay, yes, question.
Does timbre also play a role?
Yes, it definitely plays a role. Yes, it plays a role.
Voices are slightly even away, but they are all voices. As think of them together as a choir versus a piano. Even if it's playing, like the piano is playing the same pitch as one of the voices. But there are voices around the same time frequency. I might be able to separate the piano.
Yes, so there are many factors that affect these grouping cues, including, say, common onset time of notes. Or common onset time of the sound objects. If two sound objects are having a common onset, we tend to group them together through simultaneous grouping, and a common offset, and also common temporal evolution, say pitch. Yeah, energy evolution, pitch evolution, location, position evolution, and also we tend to group objects in similar locations together. We tend to group sounds with similar timbre together. Yes, yes, that's right. Yeah, there are so many factors. So in the early days, when people designed those so-called computational auditory scene analysis systems or CASA systems, people were trying to design rules for those different grouping mechanisms and use those rules to achieve source separation. But the difficulty is there are so many rules, and we don't know which rule should be used at what scenario, right? It's always a drawback of rule-based systems. You can come up with many rules, but you don't know when to apply which rule and which rule should win in what scenario.
But do you think if we are not making rule-based, we're going to like cheat learning things, that it can, like, we need much better labeling of data to get that kind of learning. Like if we just want to split sources, that's easier. But sometimes the sources become the same thing, like in our perception. So we need to label the different combinations within each audio. Like we don't have to just have the audio and the stems. We have the audio, and sometimes one stem might be grouped with another stem. Yeah,
that's exactly right. I think we are talking about a very important direction of source separation these days, which is in addition to previously people first define what source they want to separate, and then they train a model to separate it, right? But for humans, actually we define the source on the fly all the time. If for people outside of the auditorium, the whole auditorium is one source. Maybe the birds is another source, right? But for people inside of the auditorium, maybe I'm a source, you are a source, right? Maybe a musician will view each string of the instrument as a source. Other people may view the entire instrument as a source.
So you need human labelers. You can't use stems as like if you have like an input as the mixed track and stems as the output, that can do the normal source separation. But for like the realistic human source separation, we need human labelers to mix the stems together, like not just labelers, right? We need to remix the stems and then unmix them as time goes.
Yeah. Well, I see, a lot of difficulty on creating data sets for that kind of scenario, right? So now I think one way to address that is to not view it as a supervised learning problem. People are working on, for example, text-based source separation. The idea is you input some text. I want to separate the bird with a high fluctuating pitch from the many birds. I describe it and then separate the source of it. So this separation model is not trained on this separation task directly. It can be pre-trained on some kind of sound effect classification task. Say I have a sound effect detection model train on so many sound effects. And we also can train the text and the sound effect linkage model, so that when I type some text, it knows what kind of sound effect it will be linked to, right? And then with this model, we can then come to this audio mixture to see what kind of sound effect. Yeah. Yeah. That's right. Yeah, nowadays it's quite common to utilize multiple pre-trained models and compose them together to achieve some task. So yeah, knowledge can be imported into to solve the task in various ways, not only through the data annotation process for the specific task. We can actually leverage knowledge from other models and other tasks. Yeah. But very nice question. Thank you. Okay, so let's move on. In vision, we have this occlusion phenomenon. Actually, occlusion sometimes help vision perception. For example, we see a bunch of fragments, but if we know the occlusion, the ink, we see the letter B very clearly, right? In audition, we have similar phenomenon. Here we have a sine tone with a changing frequency. Okay? But there's a gap. Now let's fill the gap. The gap is filled by white noise. Now we feel the sinusoid is continuous in its pitch, right? There's no gap in the sinusoid anymore. Similarly for speech, in this example,
the state governors met with their respective legislatures convening in the capital city.
There's a gap, okay? But maybe let's listen to it again.
The state governors met with their respective legislatures convening in the capital city.
Legislatures, there's a gap. Now, if we fill the gap,
the state governors met with their respective legislatures convening in the capital city.
Okay, someone coughed at the same time, right time, and then we feel the person was not having a hiccup. Right? Another question people ask is whether those auditory scene analysis or grouping mechanisms were primitive or learned after born, right? So how did they find out? Well, they did these experiments on infants, several months old infants, and try to see whether they can achieve stream segregation. So here they play two kind of stimuli. One is high one, high two, low two, 4 tones sequence. The other one is high one, okay, high one first, and low one, high two, low one. So the order is changed. Okay. Let me play these two examples and you can tell me whether you can hear the difference. Second one. Did you hear the difference? I couldn't hear any difference, right? So that means we could not tell the order difference. I mean, we could not tell the order of the 4 tones because we segregated the 4 tones into 2 streams. And when we look at the 2 streams, okay, this one is a high tone stream alternating between high 1 to high 2. This one is also a high pitch stream alternating between high 1 and high 2. So when we segregate them into 2 streams, there's no difference between these 2 stimuli. And infants could not tell the difference either. So this suggests that infants already have the sequential grouping mechanism. Okay. Yeah, so here's a summary of the grouping cues that we use. For simultaneous grouping, we use the periodicity of the sound object to group them, and common onset, offset, common amplitude and frequency modulation. For sequential grouping, we use the proximity in frequency and time, and continuous or smooth transitions, and also related rhythm. We also use common spatial location as a grouping field. Yeah. And we know that repeated listening to stimulus can improve performance in ASA tasks. So this suggests that some cues can be learned, right, or can be improved. And we can easily follow a friend's voice than a stranger's voice in noisy environment. This also suggests that prior knowledge of the timer helps the streaming aggregation. And also music training helps analyzing music audio scenes. This suggests that prior knowledge of the music theory, composition rules, and music styles helps with stream segregation. Now, the extreme human capability, I would say, is from Mozart, right? It's a story that said that when he was 14 years old, he heard this Gregory Allegory's Misery once, okay, just once. And he was able to write it out entirely from memory and only returning to correct minor errors. This piece has 9 voices. It's very complex. IMIR grand challenge is to design algorithms to compete against Mozart. Okay, so that's the third part of the first talk. Then we can go to the music audio features quickly. So in the past several decades, people have derived a lot of music audio features. And we can categorize them into different domains. The time domain, we can compute the RMS value of the signal. We can also compute the so-called zero crossing rate, which is how often does the time domain signal changes its sign, flips its sign. It basically describes the amount of high frequency energy. And the formula is just this. We look at the sign of the signal at this sample and the sign of the signal at the previous sample and count how many changes there are. In spectral domain, we can compute spectral features from the spectrum directly, right? The linear frequency magnitude spectrum. But we can also use a Miles scale filter band. Say a Miles scale filter band can be like this. We use a triangular shaped filters where the edge of one filter is at the center of the previous filter. And the bandwidth of the filter would increase with the frequency. And then we basically have only one output from each filter. So this can reduce the linear frequency spectrum to a lower dimensional filter band response, for example, 40 dimensional. Okay. So from now on, when we talk about spectral features, we just say we compute from a spectral representation xk. This xk could be the original linear frequency spectrum, or could be a Miles filter band response, or could be a Miles scale spectrum. K is always a frequency index, but it can be different units. So we can define a lot of statistics. So we can compute the spectral centroid, which is just a gravity center of the energy. K is a frequency index, X is the amplitude or magnitude of the spectrum at the K frequency, and we compute the centroid. We can compute the spectral spread, which is, how far are the energies of different frequencies from the center frequency, from the spectral centroid. And we take the square and weight it by the energy at the frequency. We can compute higher order statistics. Say the third order spectral skewness, we look at the difference between the frequency and the center frequency's cubic power. Right? And fourth order, we look at the fourth power. It's called spectral kurtosis and so on. These features describe the spectral shape of the sound. We can also describe spectral flatness, how flat the spectrum is, or how white noise like. Right? We can use this formula. This is the it is called the metric mean, and this is the arithmetic mean. We take the ratio and take the log. And we can look at the spectral irregularity. Okay, so this is the adjacent frequency means, right? K and K plus 1, and look at the difference and square of the difference and sum over all frequencies. So the higher the value is, the more fluctuation it has.
So
yes.
Spectral flatness, does it vary to like 1 over x minus 1 over x squared non-scaling feature?
I'm not sure. I think they have different values. Yeah. I think they have different values, but I didn't check it.
Oh,
Mhm.
if it's away from white noise,
Mhm.
like my question is, does it compare to that thing for green noise and like the scale of it and to us like the tint of
You mean whether it's pink noise or what's the other one? Blue noise, right? I don't think it tells that because there's no other, right? No other information considered. So it's only about K, the frequency index, but the ordering of K is not playing any role, right? We're only looking at the distribution of it, yeah. And we can look at special roll-off. So it's the frequency when the special energy would fall quickly, start to fall quickly as the frequency increases. And special flux is the special energy change over time. So we look at at time t, the energy at frequency k, and at time t minus 1, energy at frequency k. We look at the difference. I mean, we normalize them first and then look at the difference. So this is a special flux or fluctuation over time. Okay, so those are special features. And then in music information retrieval, chroma feature is a commonly used feature. It's basically this is a spectrum, magnetic spectrum. We are trying to fold the spectrum into just one octave, so 12 beams. Now, at different octaves, we have the same pitch class. For example, C pitch class, we have C2, C3, C4. So we basically add the energy at different octaves of the same pitch class into the same beam. Okay, this is basically folding the spectrum into this 12-dimensional vector. That's chroma vector. Now you can also use a 24-dimensional vector. Say for each semitone, you use 2 beams, right, instead of 1 beam. You can also use a 36-dimensional vector to use 3 beams. These figures will show the difference between the linear frequency spectrogram. Okay, this is a piano scale from low to high, lowest note to the highest note. We can see that the fundamental frequency increases exponentially, right? Because the music scale is exponential in terms of the hertz. Okay. Now, if we change the frequency scale to log frequency scale, right? Now it's log frequency, they can be mapped to the pitch or MIDI numbers directly. Now the scale become a linear shape, right? This is the fundamental frequency. This is the overtone, the first overtone, or called second harmonic, and third harmonic, and so on. And if we fold all the octaves together into a 12-dimensional vector for each frame, then we get this chromogram. So now we have 12 dimensions along the frequency axis, and time axis is the same. We didn't change anything. Now we can see some kind of cycles, right? They correspond to different octaves of the piano scale. Okay. Now we can further normalize energy at different times, because for very low pitch notes, the energy, the harmonics will be more in the spectrum compared to the high pitch notes. So after normalization, we can see the cycling phenomenon more clearly, right? So at the higher octaves, we don't see much difference between the different octaves. So this makes the chromogram very invariant to timbre, okay, and also to pitch range. For example, this is the same piece, but played by orchestra and by piano. Okay, for 2 recordings, we compute their own chromogram. This is an orchestra recording, this is a piano recording. You can see that they are very similar, and we're going to hear this. But before we listen to it, do you know how to read a chromogram? Can you tell what piece it is? When you read it, you can focus on the high energy tones, say the red color, G, D sharp, F, D. Yes. With the keyboard, it's maybe easier, right? Let's listen to it. Now let's listen to the piano recording. Okay, you see the timbre is very different, but the chronogram are quite similar, right? So this shows the advantage of using chronogram for matching music with different timbres to achieve invariance for timbre and pitch range, instrumentation, and so on. Okay, so now more features, harmonic features. Fundamental frequency can be viewed as a harmonic feature, and we can also compute so-called inharmonicity. It's basically the average deviation of special components from perfect harmonic positions. So we have the harmonic, this is a harmonic position, h times f naught, and this is the peak frequency of the spectrum, and we can measure the deviation. And we can also compute the odd to even ratio between those harmonics, odd harmonics and even harmonics. We know certain instruments have a weaker even harmonic, for example, clarinet. We can also look at, say, tri-stimulus. This is a distribution of the energy across multiple harmonics. Say T1 would be only about the fundamental frequency A1. And T2 will be about the second harmonic, the third harmonic, and the fourth harmonic energy altogether. And T3 will be all the higher harmonics. Okay, so this is a distribution of the harmonic energy into the three groups. We can also look at the so-called harmonic structure feature, which is the vector of harmonic energy for all harmonics. Say this is a violin note, and we get these relative loudness of different harmonics. This is a clarinet note. We see these loudness for different harmonics. And for certain harmonics, we couldn't detect the harmonic because the amplitude is too low or not high enough compared to its neighboring frequency beams. Okay. So these are just the harmonic features we can use to tell the difference between instruments. And we can compute the harmonic structure feature from music mixtures directly if we know the pitch. For example, this is a mixture of multiple notes. If we know the fundamental frequency of one note, say at the red bar here, then we know the harmonic position of this note. And then we can find the closest peak to this harmonic position, say these crosses, right? And then we can compute the harmonic structure feature for this source in this mixture. This will be noisy because some of the harmonics are overlapped by other sources, but they are useful in some cases, because the overlapping situation changes all the time. At this time, maybe the second harmonic is overlapped by other sources, but in the next note, maybe the third harmonic is overlapped, but the second harmonic is not overlapped. So on average, we can have some common features for the same instrument.
This will be very sensitive to distorted.
Yes, I think so. Yeah, for distorted instruments, the harmonics change.
Because, even if it's two harmonics,
Mhm.
the distortion can have extra harmonics which will come in.
Yeah, those nonlinear transforms, yeah, that's true. Mhm. Okay, so then temporal features, we can characterize the amplitude envelope of the waveform. We can compute the takt time, so which is, how long does it take for the energy to increase from 20% of the maximum to 80% of the maximum. Here, that. We can also look at vibrato rate and depth. How fast and how much does the pitch change over time? For example, this violin note, we hear the pitch fluctuates. If we look at the pitch curve, it fluctuates. And we can compute the period or the frequency of this fluctuation, and also extent, which is the amplitude of this fluctuation in frequency. In this case, it's around 5 to 6 hertz. We can do the same thing for tremolo effects, which is the amplitude fluctuation periodically over time. And apparently, we can also compute capture features. This is a procedure. We first compute the magnitude spectrum, and then we calculate the Mel scale filter bank response, for example, using 40 filter bank. Then we take the log of the filter bank response, which is a critical step. Take the log. And then we perform discrete cosine transform on this 40D vector. And then we can choose the first several coefficients, say 15 coefficients as our feature. Yes. Vibrato is a pitch fluctuation of the note. Tremolo is the amplitude.
Difference limit for this.
Difference limit. Difference limit for vibrato. You mean like rate, vibrato rate, or or amplitude? I don't know. That's a good question. Yeah.
Maybe, but it's very different depending upon the timbre. Vocalists may do it in a particular way, violinists can do it in a different way.
Yeah, I mean, even for the same musician, they can use different vibrato rate and depth for different music passages. Yeah.
I have used the term cellular vibrato, but in Andolan and Gamma and that also depends on between what two frequencies this is vibrating. So Andolan normally has the mean frequency on one of the notes of the raga, and it's around that. But Gamma is always between two notes. It's very much context dependent. So some ragas have prescriptions of more heavy Gamma, and some are having more somber and very slow. So very typical movements are signature phrases like Tsinghua University. This is the intonation of the ga, one note. It never is stable on that note. If you want the transcription and finding threshold and tolerance, to never be found, because the entity of that intonation is that by movement. It's a very typical shape. It's not like a sinusoid. It starts very slow, then picks up, and then again slows down. And that integral, so Vanguard we used to call them as tones, like phonemes. So we used to call it's a gestalt. We can't break it down further, and that whole entity means the information of that move in the car. No.
Yeah.
Similar, more like Andolan, which is saying graph there we have it's not one note, but it's not which is a gamma, which is like a bigger tone. The pitch extent is also slow. The frequency is also slower. So that's more like
Yeah, in tremolo, I think you can control the breath to achieve the amplitude fluctuation. Also for wind instruments, you control the breath flow. Yeah.
And also many times there are examples where there is a kind of intended creation of tension or roughness before reaching a resolution. Like for example, on Rag Gurkeli, between the 5th and the -6th, it's a very slow approach, but it creates the roughness. You can kind of get the beating, but at the resolution. Is that chord? But before reaching that,
yeah,
Yeah.
drifting
Create that
there.
tension,
Mm.
but once you reach the resolution, it's very pleasant.
Mhm.
One has to have the breath control and the pitch control to achieve that state of resolution.
Ah, fascinating. Thank you. Okay, so yes, that's how we compute MFCC. And then we also use deltas of MFCC in many applications. This is temporal derivatives of the MFCC vector.
And MFCC specific for speech audio.
For speech, it's also used for music and general audio for many tasks. For example, genre classification, instrument recognition, even composer recognition from the artist recognition, those kind of things. Yeah. So here's again a brief overview of how the caption idea is derived, right? So this comes back to the source filter model. Very briefly, we can view the generated note of the instrument as the source signal or excitation signal at the this clarinet reed, and going through this filter, which is corresponding to the instrument body, it resonates to different frequencies. And in time domain, it's a convolutive process. So xt convolved with ht will give us yt. Now, in the frequency domain, it becomes multiplication, right? In the complex spectrogram or spectrum, and in the magnitude spectrum, it's also multiplication, right? But if we take the log, okay, we convert them to the decibel scale magnitude spectrum, then multiplication becomes addition. So we now have a harmonic comb, which represents the source signal, which often pretty flat, not flat, but it's not fluctuating, with a certain slope, harmonic comb. And it plus envelope. This envelope is often smoothly changing, corresponding to the resonances of this filter. And then we get this. So these dots are the new locations of the harmonics. And this is just an envelope. Okay, so at other positions, they have very small values. So we still have a harmonic comb, but the amplitude is modulated by this envelope. So now when you look at this, right, if you view this as a signal, this is the fast changing signal, okay? And it's quite periodic. You see impulses repeat by itself with, although there's some kind of amplitude change, but it's a fast changing signal. This is a slowly changing signal. This is the addition of these two signals together. Okay. Now we can so spectral envelope characterizes the timer very well. And we know that the excitation spectrum changes with pitch, but spectral envelope changes with the shape, material, and the resonance body of the filter. It does not change much with pitch. For example, we have this same spectral envelope. They correspond to the same vowel. But if we change the excitation signal, say we say the word with different pitch, right? We have different harmonic combs with different harmonic gaps. Then we get these different final spectra, but their envelopes are similar. So the question is, how do we categorize this spectral envelope? Because we're interested in features that can characterize a spectral envelope for timbre. One naive way, right, is to detect the peaks of the spectrum and then draw a smooth line to connect the peaks. Then the line is envelope, right? This is a non-parametric method. We can also use a parametric method, right? We can use maybe polynomials to represent this line that we draw, or maybe we can use sinusoidal basis to represent the line we draw, right? So the basic idea of a caption is actually to use Fourier transform to find out or to separate these two components of this frequency domain signal. As I mentioned, this final spectrum can be viewed as a linear combination or addition of these two signals. One is a fast changing signal, the other one is a slowly changing signal. Okay, and we know that Fourier transform is a linear transform. Okay, so when we transform this mixture into the Fourier domain, it equals to the Fourier transform of this excitation signal and the Fourier transform, add the Fourier transform of this signal, right? And also we know that Fourier transform separates high frequencies from low frequencies, right? So low frequencies are on the low coefficient, high frequencies are on the high coefficients. And they correspond to these two nicely. This will correspond to the low coefficients. These will correspond to the high coefficients, right? So that's the idea of capstone. We first compute this decibel scale magnitude spectrum of the signal, and then we apply Fourier transform. And then the low coefficient of the Fourier transform will correspond to the spectral envelope. The high coefficient will correspond to the excitation signal. That's it. So mathematically, this is the process. We take the time domain signal xt, we perform Fourier transform, we take the power, and we take the log to go to the decibel, log scale. And then we take an inverse Fourier transform. And then if we want to compute the power capstone, we take the power. Okay. So we have forward Fourier transform and the inverse Fourier transform here. But we do not go back to the time domain and signal because there's a log operation. Actually, this, although here we use inverse Fourier transform, we can replace it with DCT because we're dealing with real signals. When we deal with real signals, if you look at the inverse DFT, this component is canceled out. Okay, so yeah, DCT. So this is equivalent to performing DCT on the positive frequency range of the log magnitude spectrum. Yes. Yes. Yeah. Okay, I will skip the details because if you're interested, you can look at the mathematical derivation. But DCT is equivalent to inverse Fourier transform or for a DFT in this setting. So now this is interesting. We have this spectrum, the blue line, okay, and we compute the capstone, which is the Fourier transform of this spectrum. Okay, so they have the same dimensionality. Okay, and we can perform a so-called low-pass filter, right? Say taking only the low coefficient here, and we can then convert this back to the spectral domain, and that would correspond to the smooth curve, the red curve, which characterizes spectral envelope. And this process is called filtering, right? But in the textual domain, people call it liftering. Researchers were playing a letter swapping game. Filter, they change the order of FILT to LIFT to liftering. Similarly, capstone comes from letter swapping of spectrum. So SPDC is changed to CEPS. And frequency is changed to Q frequency. That's an interesting part. Okay. Do I still have some time? I think maybe 10 minutes. I can finish the feature extraction. Okay. All right. Then let's move on. So previously we have been talking about signal processing features, handcrafted features, right? We think about what physical attributes we want to compute, and then we write the equation and compute it from a signal. But in many applications, we also want to learn features directly from data. Those are called data-driven features. And for example, we can use a classification task. Okay, so not yet. So we extract features for classification for some downstream tasks, right? For example, one downstream task is a classification task. We can classify the music genre or mood or artist, or we can recognize chords from the music, or we can detect acoustic events, or recognize speech content or speaker identity. Now, the typical pipeline is we have a training phase and the testing phase. During training, we collect some training data with labels. We perform feature extraction using the features we define. And then we maybe perform some feature selection to remove redundant features and apply some feature transformation to reduce dimensionality, for example. And then we train classifier. After the classifier is trained, we put it here, and then we can apply it to the test data. So test data, we again extract the features in the same way, do the selection and transformation of the features, and then pass it through the trained classifier to get our test results or labels, prediction labels. Yes, can I take a few minutes? Okay. So the features are handcrafted, they are engineered, they're predefined. But it's hard to decide what features to use for a specific task. For example, I ask you to do maybe a music genre classification. We have talked about so many features. Which features would you use? Right? Spectral centroid, spectral flatness, or MFCC? We have no idea, right? So probably we are going to use many of them, but the dimensionality may be too high. We have to do some feature selection, transformation, and so on. So a question is, perhaps we can let computers to learn features directly from data. Then we can save the step of engineering features. And another, okay, so this is a typical pipeline for feature or representation learning. Here we start with training data. We learn the features. The features learning means that we learn a way to compute representation of the data. Okay. Once we have learned, the way is fixed, then we can apply this computation to the test data to extract the representation of the test data. And compared to the handcrafted features, this feature learning can be adapted to specific tasks. Okay. So we can use this, for example, we want to do music genre classification. We can train the feature learning module on this music genre classification task directly, and then we can learn some kind of representation for this task, and then we use this representation and apply it to some other music genre classification problems or some other data sets. So this can be adaptive. Now there are different ways for representation learning. I can use this example to explain the 3 typical ways for feature learning. This is a project about controllable voice conversion. The goal is to convert the source speaker's voice to the target speaker's timer without changing the content. But we also want the user to control the pitch and speed in a fine-grained fashion. So at any time, we can change the speed and pitch. So to do that, we have this system. We apply the source speech. We first apply the TDP SOLA, which is a signal processing-based pitch shifting and the time stretching method to apply the speed control from the user using TDP SOLA. And then we extract the pitch contour from this pitch change utterance. Okay. And then we use this block. This is the pitch embedding block to compute the pitch representation or embedding. This is a feature extractor, basically. And we feed the pitch change utterance to this block, which is a linguistic embedding block. It computes the linguistic features. It's another feature extractor. And we also take the target speaker's speech, some speech, and we pass it through this block, which is speaker embedding. It's another feature extractor. It extracts speaker-related features. And then we fuse the pitch feature of the source utterance, the linguistic content feature from the source utterance, and the speaker feature from the target speaker together, and we pass it through a vocoder to generate the converted speech. Okay. So the key here is that we utilize the 3 feature extractors, and these feature extractors are trained on tasks, other tasks. They are pre-trained on other tasks. And they are trained using different ways. Okay. So the first one, question? Yes. It's a sequence. So speaker embedding here, I don't think it's a sequence. It's a vector, although the visualization is a little misleading. Pitch embedding is a sequence. It's a pitch contour. Sorry? Yes, so I think they are of the same time resolution. so they can be concatenated together. And then the speaker embedding is concatenated to every time step of the pitch and the linguistic embeddings. That's, I believe, yeah. I don't remember the details, but I think that's a reasonable way. So for the speaker embedding, this was pre-trained on speaker classification task. The task, the training data would be pairs of speech utterances and the speaker identities. Okay, and after training, we remove the final classification prediction layer and use a second layer as the output of the feature extractor. So it's a supervised training for the feature learning in this case. Now the pitch embedding or pitch feature extractor is trained on an unsupervised task. It's a reconstruction task. It's using a vector quantized variational object encoder or VQVAE. So the task is to reconstruct the pitch contour itself, but it needs to go through a so-called bottleneck layer to compress information and going through some vector quantization steps to further compress the information. But even after quantization and compression, it needs to go back to the decoder to decode back the original pitch contour. So that's a reconstruction task. After training, we only use the encoder of this VQVAE to extract the features. And this module, with the linguistic embedding, is trained in a self-supervised learning task. So it's about mask prediction. So we mask certain regions of the utterance, or actually the hidden units of the utterance. And then we use other units to predict the masked region. That's one type of self-supervised learning. And we use this Hubert or hidden unit BERT model to train that. And I found this paper provides a very nice summary of the 5 typical ways for self-supervised learning. So self-supervised learning does not require any annotation of labels. You can train a model only on the data itself, right? But you have to create fake labels or data and fake data and fake labels. There are several ways to train. One is a transformation prediction. So for example, your data is a dog, I guess, a dog. You can rotate it with certain degrees, and you know how much you rotate. Then you feed the example to the learning machine, and you ask the machine to say, okay, it's still a dog, to predict the animal, what animal it is. It should still be a dog, and also predict the rotation angle. It should be 90 degrees. So these will provide you the supervision information, although those are created by yourself, right? This is one kind of self-supervised learning. The second one is mask prediction. Say we mask out all the other parts of the dog and only leave this leg, and you try to predict the masked region. So it's also you self-constructing supervision information. And this is instance discrimination. You have different dogs or animals, and you view each instance as a different class. You try to train a learning machine to discriminate all the different instances. That's another learning target. And this one is a clustering objective. So you have 3 different instances. For instance, you apply some transformation, say rotation, this is color change. I don't know what this is, whatever change you apply to it. And then you train a clustering module. And the target is to cluster the transformations of the same object to be into the same cluster. So you also know the target, right? And the last kind is this contrastive instance discrimination. So you have a dog and you have rotations or other transformations of this picture. Now you have another picture, okay? And you can create so-called positive and negative pairs from these pictures. Say these 2 will create a positive pair, although there are some differences, but they belong to the same category. Okay. But the first one and the third one will be a negative pair because they belong to different animals or different pictures. Then when you train a model, you try to pull together the positive pairs, but try to push apart the negative pairs. So that's another training target you can apply. So these are the different ways to train self-supervised learning models. Now you can train self-supervised learning models on huge amount of data because you don't need annotation. And after training, you can use those models to extract very powerful representations for different data, for images or audio or language. And then you can apply those features to downstream tasks. Okay, I think I'm out of time. So just brief summary of today's talk. We first gave a overview of IMIR. We talked about the different types of music data and tasks. And we also talk about the relation between IMIR and computer audition in general. We then look into auditory sensation fundamentals. We talk about auditory percepts like loudness, pitch, and timbre. We then look into some psychoacoustic experiments, specifically auditory scene analysis and those grouping mechanisms. And finally, we talk about music audio features, the handcrafted features, and also representation learning, which is what people use nowadays. With that, that's the end of the talk. Thank you very much.